Good afternoon, my name is Jacob Dayan, and today I'm going to talk about Lab 4 for Physics 2212. So for our experiment, our main goal is, so by using the principle of energy conservation and current conservation, I will predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of the unmeasurable current and potential differences in the circuits, and then examine the behavior of ohmic resistors and capacitors. And the fundamentals keys are basically conservation of energy and change, Kirchhoff's no-and-loop rule, the steady-state circuits, Ohm's law, resistors, capacitors, and series or parallel, and the capacitance. So as a summary, our results were that the actual values of the current and voltage given by the model match those predicted by the formulas, and in the RC circuit, the magnitude of the current is time-dependent based on an exponential equation. So for our models, I utilized an online ideal model for a circuit in order to observe the behaviors of resistors and capacitors in these different combinations, and their assumptions were the resistance of the wire is negligible as well as the resistance of the ammeter, and that the EMF equals the change in potential of the capacitor plus the change in potential of the resistor. So at the beginning, we distinguish about a circuit system, which is our circuit, and the surrounding, which is everything else. At the first part, we have the circuit with two batteries, two resistors, and two ammeters. We have our predictions regarding the node rule, our equations, and actual readings, and then we replace the ammeter with a voltmeter, which gives a different reading, okay? And in an open circuit, we have to know that a node current or potential difference across the opening equals that across the power source. So we then measure the potential difference across each segment, and we actually provide a claim for the loop rule where the potential difference equals 0. And then we know that the ammeter reading doesn't change because a voltmeter has very high resistance, meaning basically no current flows through it, and the path of the current in the circuit remains essentially unaltered. So as you can see in this graph, it's showing us the potential difference across certain portions of the circuit. And as you can see, across the battery went up like 3 volts, and then across both resistors, it was able to go back down to 0 volts. With the potential difference drop across the 100 ohms resistor being steeper than that of the 47 ohm resistor. So then we connect the ammeter in parallel with a 100 ohm resistor, and then we got that our current rating increases 0.06 amp, and less current comes into the contact with the 100 ohm resistor since it splits at the node, and since the ammeter has 0 ohms of resistance, the effective resistance of a portion of the circuit decreases. Okay, here we have our equations for our resistance. Okay, and we got that the results were higher than expected due to low precision of ammeter. So for the second part of the experiment, we used a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 20 millifarad capacitor. So the battery was connected to a 20 ohm bulb and the capacitor in series. And then at the beginning, the bulb started bright and then just decreased on the going out of charge. And we know that the current decreases from maximum down to 0. And then for the disconnected battery, the bulb once again lights up, and then it just decreased until it just went out of light. So it basically was discharging. And also the current decreases from maximum down to 0. Okay, and for the 10 ohm bulb, it took 10.5 seconds to charge and 2.4 seconds to discharge. And for the 20 ohm bulb, it took actually more time to charge and more time to discharge as well, as you can see. So next, I took several readings for the potential difference across the capacitor as a function of time over the course of 20 seconds. And this was the case for a 9 volt battery and a 20 millifarad capacitor and a 30 ohm light bulb. This time we found that the potential difference of the capacitors should change according to the following exponential equation, as you can see in the screen, which when relinearized produces the following, and then I graphed my data being the natural log of both sides, and just found the following line of PHYS, as you can see. So then, as you can see in the graph I explained earlier, for a 9 volt battery at 200 mF capacitor and a 30 ohm light bulb, we just calculated our time constant, which is basically resistance times capacitance, which is 30 ohm times 0.2 F equals 6 seconds. So model discrepancy. There were probably none since I used an ideal computer model of the circuit, the PHYS simulator, okay, in order to collect data and not a physical circuit model. So maybe basically that's why. And sources of error, because I use an ideal model of the circuit simulator, the only source of error maybe was like human error for me, okay, regarding charging battery or maybe not stopping timer on time. So for the discussion questions, first got what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter. So if this was the case in real life, the ammeter would have had some resistance, and because of this resistance in the real life ammeter, readings for current would likely decrease as resistance in the ammeter would contribute to the lower current, of course. And then for the second question, what if you were doing the lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? So if there were no resistor in the circuit, our ideal model would predict the capacitor to reach full charge immediately, since there would be no resistor to slow down the current. And to remove the potential difference in real life, this prediction would not have happened, since wires actually usually have some amount of resistance, so it would likely charge up more slowly than expected due to the resistance of the wires.